furnace, blazes continually in the sky, providing light and heat for 5 billion years. And it will continue to do so for 5 billion more.
Sun. If you really think about it, it's hard to underestimate the importance of the sun. After all, it's the source of all of the energy, the light, and the heat that makes life possible here on the Earth. And the sun, too, was the origin of all the planets of the solar system, including our own. The sun's really an obvious object, of course, the brightest thing in our skies. Certainly people in the past noticed it. They noticed as well that very obvious motion of the sun across the sky, make the day, and of course its disappearance at night. The sun has a subtler motion as well, however, an annual motion, and it could be most easily seen in terms of the sun's movement through the background stars. But the background stars can't be seen in the daytime, naturally. But people in the past, even in prehistoric times, very likely were aware of this annual movement of the sun. It's really just a reflection of the Earth's movement around the sun in orbit, but people in prehistoric times certainly didn't know that. But what they might have noticed is that the position of sunrise or sunset shifted along the horizon. They would have noticed as well that this movement of the sun, the change of where it rose and set and how high it was in the daytime, was somehow linked to the changes in the seasons and to the changes in the growth of vegetation, and even to the changes in visibility of the stars of the nighttime sky. Well, they realized that the sun was inextricably bound up with their lives, their own lives, and so they made a god of it. That god they worshipped, and of course we don't take sun worshipping very seriously today, but it would have made a great deal of sense back then, for it involved a recognition of the importance of the sun to human life. We don't really know when people first actually contrived a calendar of the sun and first made systematic observations of it. Certainly by the New Stone Age and the Bronze Age, they had the ability to do that. And also by then, in many parts of the world, they developed agriculture. They would have seen the reflection of the sun's annual motion, in a sense, in the planting and the growth and the harvesting of crops. And in turn, we know that they built that story of the sun's annual movement into their mythology, into their calendar, their rituals, into their holidays and their feasts. Well, we don't take sun worshipping very seriously today, of course. We take the sun for granted. But people still do pay homage to the sun at the oceans, and in the mountains, and wherever they have leisure time to do so.
The importance of the sun to life was sensed by ancient man, and so he worshipped it. The early Egyptians believed that the sun god, seated in a barge, sailed up the heavens over the back of the sky goddess in the morning and down into the arms of the god of the underworld in the evening. In Greek mythology, Helios, god of the sun, was reborn each day to drive his chariot across the skies. The Aztecs offered human sacrifices to the sun to solicit its continued blessings. Gradually, from a symbol to be worshipped, the sun became an object of intensive scientific study. During the 16th and 17th centuries, astronomers evolved new and revolutionary theories upon which today's astronomy is based. Copernicus, a Polish astronomer, explained that the Earth rotates around the sun instead of the reverse. Galileo, the Italian, first recognized that sunspots were actually on the surface of the sun. From their movement, he concluded that the sun rotates on its axis. Early telescopes were primary tools in developing and expanding this new knowledge. Today, astronomers continue to expand their knowledge with increasingly sophisticated equipment. The vertical tower of this solar observatory supports a heliostatic mirror which tracks the sun, gathers its rays, and reflects them down a light shaft that extends 300 feet below the ground. At the end of the shaft, the rays are cast back to an observing room where minute-by-minute changes across the face of the sun are observed. And projects a light beam to a spectroscope, an instrument which splits the light into its component colors, the visible spectrum. The dark lines that cut across the spectrum bands are produced by the radiation from the sun's interior shining through its atmosphere. Each line is the signature of a chemical element, such as sodium, iron, and calcium. This array of lines forms the code which describes the properties and motion of a star. By narrowing the view of the sun to a single line of the spectrum, each level of the solar atmosphere can be photographed, and each reveals a remarkably different aspect. With the addition of computer mapping and color processing that distinguishes levels of brightness, a detailed and multidimensional picture is obtained of the sun undergoing dramatic and turbulent change. The sun is a sphere of hot, seething gases and surges of radiation. Most of the light we get from the sun comes from the thin, bright layer which defines its visible edge, the photosphere. Above it, the chromosphere, a region of flaming outbursts of gas, extends through a transition zone to the thin outer atmosphere of the corona. Once thought to be a quiet layer of the solar atmosphere, the corona is now known to be a region of dramatic large-scale changes and unexpected turbulence, with temperatures reaching millions of degrees. Deep beneath the sun's atmospheric shell is the core, a violent nuclear furnace. Here, hydrogen is fused into helium, and in the process, some of the matter is converted into an enormous amount of energy. Then it convects, like a boiling liquid beneath the surface. The turbulent bubbling motion is visible in the granular cells of the photosphere. Also visible on the sun's surface are the spectacular prominences which rise to heights of more than 500,000 miles. These titanic streamers of gas are a result of the sun's equatorial regions rotating faster than the polar caps. The shearing action in the gas contorts the magnetic field into tangled structures which give rise to these eruptive actions.
Well, the sun is very different from a planet then. The sun's primarily gaseous. In fact, most of it is hydrogen gas, the lightest of the elements. 60 to 80% of the sun is made of hydrogen. And most of the rest of it is the next lightest element, helium. Together, hydrogen and helium make up somewhere between 96 to 99% of the material in the sun. The rest of it is simply the rest of the heavy elements, the kinds of things we find most common on planets like the Earth. The sun's a lot more massive than the Earth is as well. In fact, it contains about 333,000 times as much material as the Earth does. And that material is not as dense as the material on the Earth. The average density of the sun is only about half again as dense as water. The sun naturally gives off light whereas a planet like the Earth reflects light. And the sun gives off light in all colors of the electromagnetic spectrum. Of course, our eyes are most sensitive to visible light, and that's the kind of light, of course, that we see when we look at the rainbow of colors from violet through red. It's no accident at all that our eyes have evolved to be sensitive to the kind of light that the sun gives most of, the kind that reaches us here on the surface of the Earth. But the sun does emit light in other colors, X-rays, ultraviolet rays, as well as infrared, and so on. We detect these with instruments, some of which we send up into space. But whether we're catching the light from the sun, from space vehicles, or here on the Earth, that light from the sun has a great distance to travel before it reaches us. On the average, the sun is 150 million kilometers from the Earth. That means it takes light emitted by the sun 8 minutes to reach us here on the Earth. So if the sun were to go out right now, we'd have another 8 minutes of grace before we knew it.
One of the most awe-inspiring natural events is a total eclipse of the sun. This occurs when the moon, at the phase of a new moon, passes directly between the sun and the Earth and covers up the sun. Total solar eclipses occur on the average about every year and a half.
When an eclipse occurs, the moon covers the bright surface of the sun, and then we can see the gases surrounding the sun, the solar atmosphere, as it were. Normally, the light of the sun itself is so bright that we can't see any of the stuff nearby. The most remarkable and obvious thing that we see is a great pearly cloud around the sun going out to perhaps 5 solar radii, which is called the solar corona, corona meaning crown.
The dark areas across the solar disk are coronal holes, which may provide new clues to the sun's interior and may also be the source of the solar wind that blows outward to the farthest planets.
Coronal holes are now known to be the source of high-speed solar wind streams. The sun, because its outer atmosphere is very hot, is essentially evaporating off material, just like steam evaporates from a boiling pot of water. This material is blowing away from the sun at fairly high speeds. Coronal holes are areas which are open to interplanetary space. The magnetic field associated with coronal holes is open. Elsewhere in the corona, the magnetic field is relatively closed. The material, although it's coming up from below, cannot escape to interplanetary space. But coronal holes are important because that's where the magnetic field is open to space, and that's where material can flow away from the sun very readily. In 1973, the Skylab satellite was launched, and there was a telescope on board that satellite which allowed us to see the corona against the disk. This is only possible from space. The coronal holes immediately became very prominently visible as dark regions in the corona, such as this one in the lower right. Observations like this were made on a regular basis from Skylab for a period of 9 months and showed very conclusively that the high-speed solar wind does come from these regions of the coronal holes.
Now, the corona is very much hotter, 1,000,000 degrees or so, and in fact, it is so hot that the sun's gravity cannot hold on to the material in the corona, but it streams outward in what we call the solar wind. And remember, the Earth is only 214 solar radii away from the sun. So in terms of the scale of the sun, that's really not so much. And this gas flows on out and finally flows around the Earth. Now, the Earth has a magnetic field, so its magnetic field shields it to a certain extent against this flow, and the flow of gas in the solar wind just goes right around the Earth and then goes on past it, and there's a great tail or plume behind the Earth as the magnetic field of the Earth is strung out by the solar wind. So we are, in fact, sampling all the time on the Earth the flow of material from the sun.
We see that the sun can be very active far from the photosphere. The corona expands out into space to produce the solar wind. We now realize that the solar wind may actually emerge from the coronal holes. But there's activity on the photosphere of the sun as well. Sunspots, for example. And if a sunspot is large enough, as they sometimes grow, it can be seen from the Earth without the help of a telescope. fact, we believe that there's evidence that the Chinese in ancient times recorded sunspots. And it was Galileo that showed that sunspots were actually on the sun and not in the Earth's atmosphere or somewhere between the Earth and the sun. We also now know that sunspots have an 11-year cycle. That is, they go from a time of maximum number of spots on the face of the sun to a minimum number and back to maximum again in about 11 years. Actually, it's a 22-year cycle because of reversals of magnetic effects. Now, around the turn of the century, Walter Maunder, an astronomer, discovered something interesting about the history of sunspots. He found that from 1645 to 1715, there were really no records of sunspots. Now, there were people who were capable of observing the sun at that time, and they were looking for sunspots, and yet it appears they didn't find any. Also through this period, the aurora was rarely seen, and for that matter, during total solar eclipses, the corona seemed unusually weak. Well, for a 70-year period, an unprecedented length of time, it seems as though most of the cycles of solar activity simply ceased to operate. What's even more interesting is that this time coincided with a mini ice age in Europe, as well as with an extensive drought over the southwestern United States. Yet these facts were forgotten until, rather recently, when a solar physicist, Dr. John Eddy, became interested in the problem again. And they're especially interesting to us today because they may be clues of the relationship between the cycles of solar activity and the climate here on Earth.
Sunspots, regions of intense magnetic activity, appear on the surface, disappear in a few hours, or grow and persist for months in a mysterious 11-year cycle. They seem dark only because the surrounding area is so bright. Some sunspots may cover hundreds of millions of square miles. Here, a giant spot dwarfs a circle the size of the Earth. These photographs, taken on 11 successive days, show the movement of the spots across the face of the sun. By keeping a careful check on the number and location of sunspots, astronomers discover that they follow a regular cycle. The cycle begins with the appearance of a few spots in the northern and southern latitudes of the sun. In time, more spots appear closer and closer to the sun's equator. Later still, the spots decrease until few or none remain. From beginning to end, this cycle averages about 11 years. Strong magnetic fields are known to be involved. The nature of these fields is not fully understood. Sunspots usually appear in pairs, and it has been noticed that one of them has a positive magnetic pole while the other is negative, as if a horseshoe magnet were buried in the sun.
One rather remarkable thing we've found is that, you know, the normal sunspot has a normal magnetic pole for that 11-year cycle. That is, in one hemisphere, the north poles are always leading, the south poles are always following. Every once in a while you get a sunspot that is twisted around. You know, it's born bad, and instead of the North Pole leading, the South Pole is leading. And there is something wrong with that. It tries to twist itself back to the proper configuration. We don't know what the forces are that are pushing this. As it twists itself around, great energy is released. Now, an example of that was the great active region of August 1972. This region produced 3 of the greatest solar flares ever observed within about a 5-day period, and its magnetic polarity was totally reversed. So we were able to tell ahead of time that it indeed was likely to have large solar flares, and it did.
The greatest explosions in the solar system are flares, intense bursts of light erupting with the force of billions of hydrogen bombs. They move at hundreds of miles a second. Then, after minutes or hours, they fade away. Seen against the sun's disk, a flare may light 50 million square miles of the sun's surface to several times its normal brilliance in hydrogen light. Flares occur low in the sun's atmosphere, usually above a sunspot. The sunspot's magnetic field changes abruptly at the time of the flare, involving enormous energy changes. Both particles and wave radiations are emitted, which reach the Earth and spiral in toward the magnetic poles. Here they interact in a complex way with molecules in the Earth's atmosphere. The atmosphere then glows like gas in a neon tube, creating the aurora, the northern or southern lights. These shimmering draperies in the night sky, greatly speeded up here in time-lapse films, occur at heights ranging from 60 to 500 miles.
One problem with observing the sun is that as the sun shines down on us, it heats the ground. And most of you have noticed that on a typical summer day, we get a very rapid buildup of clouds. That's produced by convection from the ground. If any of you have looked at a Great Lake, for example, from an airplane, you'll see that lakes tend not to be covered by summertime cloudiness, and that is because water has a high specific heat and stays cool even while the sun is heating it. Now, the reason we are worried about this in astronomy is we want to see the very finest details on the sun, because it's so far away that the smallest thing we can see on the sun is maybe 300 or 400 kilometers across, the size of the state of California. So we need to have telescopes which can resolve down to a half an arc second. That's the same as looking at a man standing on top of a hotel in San Francisco from Los Angeles. It's very difficult to do. We can build the telescopes to do it, but the atmosphere interferes with us, the rippling and shimmering of the atmosphere. That's particularly bad for solar astronomers because we have the hot air rising from the ground. And for that reason, we built the Big Bear Solar Observatory in the middle of Big Bear Lake, where the water stays relatively cool all day, even though the sun is shining down on it, and we are not disturbed by convection currents rising from the ground.
Solar research has recently taken tremendous strides with orbiting solar observatories. The sensors on these observatories scan the sun very slowly. In this case, X-ray and ultraviolet spectrometers return data which can be visualized. With the help of a computer, these solar maps provide a picture of the sun's surface, its temperatures, and its thermonuclear behavior.
These solar exploration missions are becoming more and more important. There's evidence that random fluctuations in the convection of the sun's internal fluids, internal gases, just these random fluctuations cause variation in the amount of light the sun puts out, the amount of energy, the solar constant, of the order of 1% over a 10-year to 100-year period. Sounds very little. That 1% can cause enormous climatic changes on the Earth. In order for us to predict, to understand the changes of the climate on the Earth, we must be able to have more detailed measurements of the surface of the sun. Some of these information is just coming out now. We used to think that looking at the sun this close up was just a scientific exercise. It's not. It's a considerable application value.
Solar research is vital to our ability to control physical conditions on this planet. During solar eruptions, countless needles on airplanes may swing erratically. Ship communications might black out, and our ability to predict such eruptions could help prevent potential tragedies. Major weather predictions might be possible if the sun's activity could be explained. Solar exploration is an attempt to explain and understand some of these mysteries. Mysteries which vitally affect every planet in the solar system, every form of life on Earth.